Okay, we can start. This is lecture number 2 on numerical. This is our second lecture in numerical analysis. As such, so under this lecture, this is part. We'll look at 2 parts, which is elementary row operations on matrices and inverse of a matrix. In this scenario, we'll be looking at the inverse of a matrix. We'll be finding the inverse of a given matrix using the Gaussian-Jordan elimination method, or rather using the row operation methods, not where you find the inverse of a matrix via the determinant method, no. So we'll be using the elementary row operations. Now, let's start with this definition about elementary row operations. Okay, let's look at the matrix A. This matrix A be some matrix, some n by n matrix on the field K. Then the following are called the elementary row operations on matrix A. These which I've listed are called the elementary row operations on matrix A. The first one is that if 1 is less than the I, which is less than m, that is the rows. If 1 is less than the I, which is less than or equal to the m, and alpha is some constant with A not being equal to 0. Remember, this matrix A has entries Aij, with n of those not being equal to 0, then you multiply the ith row of A by alpha. You multiply the ith row of A by alpha. The ith row, any row of a given matrix by some any scalar. Alpha is any scalar number. It can be a complex number or it can be a real number, so it doesn't matter. Then, if you remember, this I is the number of rows of the matrix Aij, of the matrix A with entries Aij, and M, remember, is the total number of rows. So now the other one is the matrix. But this is number 2. If 1 is less than or equal to I or J, which is less than or equal to M, then I is not equal to J. So the number of rows, the ith row is not equal to the jth column, and alpha is some constant. In this case, you add alpha times the jth row to the ith row. So the I and J in this second part, we assume them to be rows. So then in this scenario, if this is the situation, then you're going to add alpha times the jth row to the ith row. The next one is, you can also interchange the ith row and jth row. So it's a scenario where you can interchange the rows. Row 1, you interchange it with row 2. So that's why we are just calling them ith row and the jth row. So now, all these statements that I've mentioned, all these statements 1, 2, and 3, what I mean is what I'm writing down here. What I mean is what I'm writing, what is written down. So now, if Ri, where I runs from 1 up to m, if Ri, where I runs from 1 up to m, are the m rows of matrix A, if these are the number of rows, if the matrix has m rows, for example, it has 5 rows, 10 columns, 5 rows, 6 rows, 20 rows, or 100 rows, then their elementary row operations are written as follows. So what the first one, in short, I'm just trying to make it clear. What the first one is trying to say is that row 1, you can change it to alpha times row 1. And also you can replace row I. This is row I. Row I is the same as alpha times row I. So what you have done, what you're doing is you're applying an elementary operation on the rows of a given matrix. That's why you got elementary row operations on matrices. The second one is you can replace row I by row I plus alpha row j, this is what the statement number 2 is trying to tell us. So row I, you can replace it by row I plus alpha row j. That's what I'm saying. You add alpha times the jth row to the ith row, which is this one. Then you can also interchange, you swap them. You can interchange row I by row j. You can interchange row I by the jth row. Now, let's look at, that is about definition number 1. It's talking about elementary row operations. Now, let's go to the second definition number 2. What is definition number 2 really talking about? So, definition number 2 is talking about row equivalent matrices. From an elementary row operation, then now we are coming to these are the operations that you can these are the types of operations that you can work on any given matrix. Doesn't matter whether the given matrix is an invertible matrix or the given matrix is a square matrix or it's a non-square matrix. These operations can apply on them. Now, from which we can now come to this definition number 2. Definition number 2 is talking about row equivalent matrices. When are two matrices said to be row equivalent? This is what definition number 2 is trying to tell us. After we have talked about row operations on a given matrix, so whenever you apply this row operation on the first matrix, the second matrix that you're going to get will not be the same as the first matrix on which you applied the row operations. So you have this matrix A, and then you multiply the first row, for example, the first row by maybe 3. Definitely, the resulting matrix that you're going to get will not be exactly the same as the first matrix. So now, there will be this new matrix that you're going to get. So that matrix that you have found by applying the row operation on the first matrix, the new matrix, we call it its row equivalent to the first matrix. So this is what this definition number 2 is talking about. So if we have an m by n matrix A and an m by n matrix B, then we say that A and B are said to be row equivalent or row equivalent matrices if one can be obtained from another by applying a finite sequence of elementary row operations. You apply a finite sequence of elementary row operations. We have not said infinite here, finite. So you have this matrix, first matrix, and you have the second matrix. Now, these two matrices are row equivalent if any of them you are obtaining it from the other by applying a finite sequence of elementary row operations. Then we say these two matrices are row equivalent. Now, an example this example number 3. So what example number 3 is trying to do is just trying to explain to us what definition number 2 is talking about. So now, if you look at the same, prove that the matrix A, which has with these entries, is row equivalent to the matrix B with these entries. The matrix A is row equivalent to the matrix B. Now, if you look at the matrix A and the matrix B, the only which rows are different from each other. The first rows are the same. The only rows which are different from each other are row number 1 and number 2. So row number 1 and number 2 in matrix B is different from row number 1. From row number 2 and row number 3 in matrix A. So row number 2 and number 3 in matrix B is different from row number 2 and 1 in matrix A. Now, how can we move from matrix A to matrix B? We want to obtain matrix B from matrix A by applying an elementary row operations. Now, to do this, The question is, sometimes you cannot tell how many elementary row operations you can apply on the first matrix so that you can arrive on your second matrix that you've been given. So you have to make sure that you see the matrices, look at their similarities, what has really gone, what has changed in these two matrices from the first one to the second one, or from the second one to the first one. So you need to have all those kind of reasoning. So now, let's go to this one. So if we are moving from matrix A to matrix B. So our matrix A is this matrix. Now, let's look at row number 2 of matrix B and row number 2 of matrix A. If you look at these matrices, you see row number 2 of matrix B and row number 2 of matrix A. Now, they are different. But if you look at row number 2 of matrix B and row number 3 of matrix A, you look at row number 2 of matrix B and row number 3 of matrix A, they are the same. Now, how can I shift this? Maybe before I even go to that, I think we are supposed to start with the same one, but anyway, we can even start with N. You can start by interchanging the rows or by changing row 2 in matrix A. So in this scenario, we started by changing row 2 of matrix A. Now, let's look at matrix A. So let's change row 2, let's make row 2 to be equal to row 1 plus 2 times row 3. Row 2 is equal to row 1 plus 2 times row 3. Sorry, this was supposed to be not row 1. This was supposed to be, it was supposed to be row 2 implies row 2 plus 2 times row 3, not row 1 here. You can't, that's not how we do the elementary row operations. So you say row 2, you substitute by row 2 plus a constant and the ith row. So here it was supposed to be row 2. I'll try to make changes in that vein. So now, so we are saying, so what we are doing is, in matrix A, all the entries in row 1, we are going to replace them by adding the first entry is in row 1 by 2 times the first entry in row 3. Now, if you look in row 3, we have negative 1. Let's start with the first column. In row 3, the first entry is negative 1. In row 2, the first entry is 2. So what you're going to do is, you're going to say this is the same as 2 plus 2 times negative 1. Here we are going to have 2 plus 2 times negative 1. So if you say 2 plus 2 times negative 1, this is going to give us 2 minus 2, which will give us 0, which is this one. Again, you go in the second column. So we have 1 plus 2 times 1. We are going to have 1 plus 2, because it is 2 times row 3. So it is going to be 1 plus 2 times 1. Now 1 plus 2 times 1 to give us a 3. The next one, it will be 0 plus 2 times 0, which will just give us a 0, and 1 plus 2 times 2, so it will be 2 times 2. So it will be 1 plus 2 times 2, which will give us a 5. So we have moved, we have applied, we have changed the picture of row 1, the bigger picture of row 2, sorry, we have changed it to this row by applying an elementary row operation. From here now, then we'll check, okay, our resulting matrix, this 0, 3, 0, 5 is in third row. And this negative 1, 1, 0, 2 is in here, it's in second row, in B. So the only thing that we need to do here now, we are in the middle of this operation. So the only thing that we need to do, we need to interchange row 2 and with respect to row 3. When we interchange row 2 and row 3, what you are going to get is the matrix B. So what we have done, we have applied an elementary row operation on matrix A to come up with matrix B. In this scenario now, we are saying matrix B and matrix A are row equivalent matrices, or matrix A is row equivalent to matrix B, or matrix B is row equivalent to matrix A. So this is about row equivalence between matrices. Okay, let's go to the next definition, you know, there are row equivalent matrices, and there's also row operations on matrices. Then now, what this definition is saturated at one point, so I'll try to space them so that you can, when studying, you can have a bigger picture. Okay, now, so we have this scenario. We have what we call a row echelon form. Every matrix can be converted into a row echelon form. So a matrix can be converted into a row echelon form and also a reduced row echelon form. There is a row echelon form and a reduced row echelon form. So these are two properties. So if we have a matrix A, let's have a matrix, an m by n matrix A, which is being a rectangular matrix over the field K. So we have this matrix, which is a rectangular matrix over a field K. Remember, we have upper, it's rectangular. That means in short, it's a square matrix. Now, this matrix is said to be in a row echelon form, if all of the following conditions are satisfied. These three conditions should be satisfied. The first three, not 4 and 5. I mean the first three. The first condition is the first non-zero element in any non-zero row is a 1. The first non-zero element in any non-zero row is 1. You know, this statement, I'll show you in the example. The second one is rows are arranged so that the columns contain the first non-zero elements. Rows are arranged, these rows, you arrange them so that the column containing the first non-zero element, remember, you arrange these rows, and so that as you are arranging these rows, you should put in mind that the columns containing the first non-zero element in any row is to the left of the column containing the first non-zero number of the next row. The third property, all rows consisting entirely of zeros appear at the bottom of the matrix. What does this mean? So if you have any row whose entries are zeros, this row, the entries, all of them are zeros, you push them at the bottom. Now, that's about row echelon form. Then you say this matrix is in row echelon form. Now, if a matrix is in echelon form, if you have a matrix which is already in row echelon form, and it satisfies the following condition, then it is